Alright, so we are continuing with oscillations. We are still calculating position, velocity, acceleration of simple harmonic motion systems, and looking at combining it with principles of momentum and collisions. So before I jump in, I want to take a look at our period of a pendulum formula again, just to point out it doesn't matter how much mass you have in a pendulum. It also doesn't matter how far away from equilibrium you pull the pendulum. It just matters what the length of the pendulum is and what gravity is. So that means as long as you do have the same length of the lever arm and gravity is the same, so if you're on Earth, you could pull a pendulum 1 meter back and swing it, and the period would be the same as if you pulled it 3 meters back and swung it. It's kind of cool. Not very intuitive. Okay, so I'm going to do this a little bit differently, and I'm going to have you and I kind of talk through this as we go, and then I'll flash answers for each part as we go. So I've got our first block of 2 times our mass collides into a second block of 1 times our mass on a spring. The table is frictionless and it has a spring constant of k. I want expressions for v, the speed of the block immediately after impact. What do I have to do?
So speed. We use conservation of momentum.
Okay, how much momentum did I have beforehand?
It's 2 mv initial.
Okay, right?
Wait, how can I make this big? Oh, never mind, I did it.
Okay, 2 mv initial. And then immediately after they touch, what will happen?
It's 3 mv final. They attach together.
Okay, cool. So we can solve for v final. As 2/3 VO over VF. Oh, sorry, 2/3
Yes.
VO is VF. Okay. So with that first one, actually I'm going to go on this one because it's a little bit bigger. How can I find the maximum distance that the spring is compressed?
That's when all the kinetic energy is converted to elastic potential energy, so it's 1/2 mv squared plus is equal to 1/2 kx squared, but for B we use the one that we solved from A.
Okay, sounds good. So what's my mass right now?
2m. No, wait. Maximum distance. Oh, it's 2m.
Okay,
Isn't
so
it?
this is actually my kinetic energy for the entire 3m that touched the spring.
Oh, yeah, 3m and 2 v initial over 3.
Okay. Then we can solve for our x. So I'll multiply by 2, divide by k. And this will give me 2m VO over k. And then I can take the square root. Okay, and then what can I do for a period?
Period for the spring is 2 pi square root.
Oh, wait,
And
hold on, sorry. There's the minute mistake here. This is v squared.
Oh yeah. So it's 4 over 9 and then 3, 3. So 4 over 3.
V. Okay, I'm gonna pull out that VO. And I'm gonna pull out a 2 as well. Since that would have been VO squared underneath the root.
Mm-hmm.
Okay, cool. We'll check 2V over 3. 2V. One of those three's cancelled. Okay. I think we're good. I think my other side has it wrong actually. So this should be 1, 3 on the bottom. So our top 3 already cancelled. Okay. How about my period?
It's 2 pi square root m over k.
Okay,
And
what's
then
our
m is 3. 3m.
M is 3M. Okay.
Oh, we just leave it like this? Oh yeah.
Yep, that's all I asked for.
Okay.
So,
Yeah.
okay. And then last one. So I've got ideal massless spring and then a pan suspensions. This is just like a hook, and then there's a pan at the bottom.
Mm-hmm.
Okay. There's a piece of clay that's mass m, so same mass as the pan, dropped from a height h and then sticks to it. I want to determine the speed of the clay at the instant it hits the pan.
So it's conservation of energy.
Okay. So
Speed.
kinetic energy equals potential.
Mm-hmm. So, yeah, it's equal to mgh.
Okay, in this case that is the whole h. Okay.
Mm-hmm. Square root 2gh.
Awesome. And then I need the speed of the clay and the pan just after the clay strikes it.
Speed. So this one is conservation of momentum.
Mm-hmm. Conservation of momentum. How much momentum did we have before the clay hits the pan?
That's just mv initial.
Okay. I already labeled that as VF last time, so I'm going to keep labeling that VF, and then I'll label maybe a VF2 afterwards. Okay.
Is equal to 2m. V final. It should be a different V.
Yeah, I'm going to sub it F2.
Yeah.
Okay.
Then we plug in V final from the one that we solved in question 8. So it's m square root 2gh.
My m's are going to cancel. So this would
Yep.
be root 2gh over 2 is equal to
Yes.
VF2.
Mm-hmm.
Okay. Then we come to equilibrium at a distance h over 2 below the current position. I want to determine the spring constant of the attached spring.
So spring constant. That's when all the kinetic energy, potential energy.
Okay, there's a spring constant in our potential energy of a spring formula.
Wait, that's when we use conservation of energy, right?
Okay, it is conservation of energy. We've got something weird happening though, because we had both kinetic energy and potential energy when this mass of clay first hit the block, right?
Oh yeah, so that's when mgh.
Ah, sorry. K plus U gravity equals.
U spring.
Okay. What's this kinetic energy?
1/2 mv square, but v is from A, right?
V is from before we hit the pan or after we hit the pan?
Before.
Okay. So I'm going to call this V initial.
Mm-hmm. Plus mgh.
Okay. I don't think this should be before we hit the pan. I think this needs to be after,
Oh yeah.
because then we're going to have both of our masses combined. So we need kinetic energy right after we hit the pan, like immediately after we hit the pan. Then we still have potential energy for those two masses though, 2m. Okay, so I'm going to go back. This is VF then. Okay. So if that's true and both masses are here, then how far do we drop?
mgh.
Okay, this will be mgh. I'm trying to figure out what h is though. So how far does the
Oh,
pan
h
drop?
over 2
H over 2. Okay, so this is mgh over 2. And
is
then,
equal to 1/2 kx square.
okay, what's our x?
H over 2.
H over 2 squared. Okay, so now I don't have any x's. We should be able to solve for k.
Yeah.
So I'm going to sub. This would be 1/2 m times our vf.
Is from B.
Right. So that was... Oop,
So
that was
it's
actually f2
square.
for us, is here. Because that was how we
Yeah.
combined. So that's...
2gh over 4. So that's 1/2 gh over 2.
Okay.
Is plus mgh over 2 is equal to h 8 kh square over 8.
Oops, yeah. Forgot that one half on the outside. Okay. So,
And then 1/2 cancel out. Also, if it is just mgh.
right. So it's really just mgh, but I've got those constants up there.
And then we divide by height square and times 8. So that's 8 mgh over h square.
Okay. So I've got... this, right?
Mm-hmm.
Okay. So 6mgh over h squared equals k. And then 1h will cancel. So 6mg over h I've got. Okay. Do the same thing?
Mm-hmm.
Oh.
Oh, D?
So I've got 12. Hold on, so that means I messed up something. Um,
it disappeared.
Okay, I'm not seeing what we did wrong. I'm gonna go through this one, see if I can find it. So VF2, we plugged in, okay. I think we did the same thing. 2M. Did we do that? I might not have replaced the masses. I didn't replace the masses. Okay. So what should these masses be?
Man, that's 2M.
Right. Okay, so this I can pull out a 2. And then this will be the same as what we had last time.
Mm-hmm.
Will give me 12 mg over h. Okay, and now we match. And last one, determine the period of oscillation.
Period of the oscillation. Oh, that's spring, so that's 2m square root 2m, the 2 pi square root 2 pi over k.
2 pi square root.
2 pi, isn't it? No, 2m.
Okay, so my general form is 2 pi m over k. But you're right, for us this is going to be 2 pi root
Over
2m, because we've got 2
2m,
masses
then
over
k.
our k, which is here.
Uh-huh.
12 mg over h. Okay, then we just need to simplify.
Yeah, so 6 12 1 over 6, and then 1 no m cancel out,
M will
right?
cancel out.
So it's just 1 over 6g.
Oh, I've got one more thing.
G? No. What is the bottom one, isn't it?
That's h.
Oh, h.
So that should go on top.
Yep.
Okay. Any questions on anything we did so far?
Nope.
Okay. So that's it for today. I've got 2 free response questions that I want you to finish before our next class for physics. So I've linked both of those in the Skype and the WeChat, and I'll upload them to course sites shortly.
Mm-hmm.
All right, thank you so much for coming.